lectures that Whit and I are giving, and I'm giving both today. So we'll be talking about dynamic programming. Sort of a slightly different view than you might have seen in your undergraduate algorithms course, because we're going to be sticking to purely functional setting, again, because it's safe for parallelism. Although that's maybe a little white lie in the sense that what we're going to do is we're going to actually, under the hood, add some non-functional features to properly support dynamic programming. Okay, as you probably know, you can implement dynamic programming with memoization. And so what we're going to do is we're going to hide some side effects under the hood. So the point being is, if you're a programmer of this methodology, you're not going to see those side effects. It's going to act like it's pure. But if you're an implementer, you're going to then do these. In fact, some of the data structures that are used under the hood here are quite sophisticated concurrent data structures. And I'm not going to spend much time talking about them, but I'll at least mention what's needed. So it's sort of like the case when we talked about the sequences with fast updates, where we said under the hood they're implemented in a non-functional way, but from the point of view of the programmer, they look purely functional. And again, you also need a cost model here, and I'm not going to actually have time to talk much about the cost model, but it'll be sort of obvious. I'm not going to write down the rules formally, but you can come up with a cost model, which again is a slightly non-functional under the hood, but is quite easy to reason about. So that's the topic. So what is dynamic programming? So it's, okay. It's basically recursion with sharing, right? Or maybe you might call it divide and conquer with sharing. Okay, so it's very similar to the other inductive techniques like divide and conquer. We're going to make multiple recursive calls on smaller instances to make sure our induction works, and then somehow put those together. So like in divide and conquer, we might have some work to divide a problem up. In dynamic programming, that's typically pretty easy to divide it up. You make some recursive calls on smaller instances of the problem, and then you bring them back and you put them together in some way. And the only difference is that these recursive calls are shared in the sense that multiple people could make the same call on the same input arguments, and we want to make sure that we don't redundantly evaluate those, and we make good use of sharing. So a lot of the approaches we've talked about in this class are basically inductive approaches. Of course, divide and conquer is inductive, which makes them very nice for functional languages because it's all compositional. We prove the correctness of the pieces. We use it to prove the correctness of the whole thing. So certainly contraction is inductive. Divide and conquer is inductive. Dynamic programming is. And the other one, which we're not actually talking about in these lectures, is the greedy method. That can be thought of as an inductive technique where you sort of remove one element, solve it on a problem that's one smaller, and then that gives you the total solution. Okay, so what is the recipe that we're going to be looking at for dynamic programming? Okay, the first thing is we're going to come up with a recursive solution to our problem. Okay, and the way that we're going to know it's dynamic programming as opposed to just a standard divide and conquer is we're going to recognize that some of the function calls we call, we're making have the same arguments coming from different calls, from different locations in our recursion tree. And so there's some possibility for sharing. Okay. And then what we're going to do is we want to know what the costs of our algorithms are. We're going to calculate the span. And what's interesting is we can calculate the span of these programs based on the recursive solution without worrying about sharing. Okay, it turns out the span is unaffected by sharing. Okay, so if we don't share, what happens is the work might be exponential, that the work is going to reduce significantly by sharing, but the span is unaffected. So we can just look at our recursive solution, and even though it's not work efficient, we can calculate the span from it. And we'll look at examples of that. And third is we calculate the work. And I should point out most dynamic programs are quite parallel. We'll see several examples. In fact, only the first example I'm going to do, because it's trivial, is not parallel. So to calculate the work, we basically identify unique calls, and then we determine cost of each. And most of the time we can just multiply this. We can figure out how much each unique call costs, and we can then determine the cost of each of them and just multiply those, and that gives us the work. Okay, so by unique function calls, I mean ones which have the same arguments, and we'll talk a little bit more about that. And then that gives us our solution of the work. So this is most of the case. Now it could be that the cost of each one differs widely. I actually don't know any of examples where that's the case. I don't know any examples where we can't just simply multiply this. But in theory, not all of these calls might have the same cost, and so we might have to do some more complicated analysis there. But like I said, I've not come across such a case. Yeah? Yeah.
So where we are going to reduce cost from sharing, because there would be a communication, right, if there is a sharing?
Yeah, so that's when we get into the implementation, we'll talk a little bit about the cost of sharing. Okay. And so there might be some cost. It depends on how you implement it, et cetera. Oh, I should say, in this class, we're going to limit ourselves to make things easier. We're going to limit ourselves to function with integer arguments. Okay. Now you can often convert something that's not an integer argument. For example, if you have a sequence, you could convert, and you want to take a subsequence, you convert it to the two endpoints, which are integers of the sequence. But the purpose of having integer arguments is it makes it easier to test for equality. So there is a little question here. What does it mean to be shared? Okay, there's this notion of equality in there, that the arguments are, you have to talk about equality. And for those of you who have maybe had more advanced courses in programming languages, might realize that just the question of equality itself is non-trivial. Okay, and it's not obvious. Like if I give you two functions, right? Are they equal or not, right? Maybe they return the same things, or maybe it's not even decidable whether they return the same things, right, given the same arguments. So equality is a little bit of a fishy thing, so we're just going to stick with integer arguments. But we could basically replace this with any argument that we know we have an equality on. Okay, and furthermore, for efficiency, getting to your question, we want more than just equality on those arguments. We want some way to hash them, because we're going to be storing these values in a hash table so that we can quickly look them up, and so we might want a hash function. And so certainly if they're integers, we both have equality in integers, and it's easy to generate a hash function. So we'll stick to that. Okay, so let's go through a bunch of examples. What's the simplest example of a dynamic program that many of you might have seen? Fibonacci, good. So let's do the genetic hello world of dynamic programming, right? So we have fib of n equals, and I'm going to be assuming, Fibonacci's numbers are 1, 1, 2, 3, 5, 8, etc. I'll number them. This is 0, 1, 2, 3, 4. So this is our 0th one, our first one, etc. So we have something like if n is less than or equal to 1, then 1. Else fib of n minus 2 plus fib n minus 1. Okay, so that's our dynamic programming. Now you might say that's a recursive program, but my worldview here is I view that as a dynamic program already because we can figure out this sharing on our own and figure out what the work and span are going to be. So that's our recursive solution. It's got an integer argument. Okay, we can now calculate the span. So what's the span of this? N. Right, because we're going to have, if you look at the recursion tree, right, we're going to start with n, and we're going to have n minus 1, n minus 2, etc. And the longest path along here, this leftmost branch here, is going to have depth n. It's decreasing by 1 on each step. Okay, we're done. That's a span. That's a span of both the one with sharing and without sharing. It makes no difference. Okay. Now, it turns out that this particular example is not parallel, so the work is also going to be order n, and we're not going to gain much parallelism, but we'll see in all the other examples we cover there will be parallelism. So then we ask, well, we want to identify the unique function calls. So we want to say that if I do a fib on 7, it's a fib on 7, I'm only going to count it once. So how many unique function calls are there on fib of n? N, right? So if we look at work equals n unique calls, and what's the cost of each of these calls? Again, we're not going to count the cost of the scheduling or the overhead or anything. It's order 1, because what I'm saying, by cost I mean, it's like when we analyze divide and conquer, we say there's a cost of the 2 recursive calls plus the cost we do in the routine itself, right? So I'm not including these 2 costs, I'm including everything else, the rest, okay? And so the cost of the rest is, well, I got a plus, a comparison, a return, and a function call, some small amount, some constant, right? Times order 1, so that's order n. Okay, we're done. Okay, so that's the analysis of that one dynamic program.
Sorry, I know it doesn't change the order, but why is it not 2n?
Why is it not 2n? So what would the 2n unique calls be?
Your calls to fib, right?
Yeah. Mm-hmm.
So each time you call fib, you're calling fib n minus 2 and minus 1.
So I mean with unique different, how many different arguments? Maybe that's the way I should say, not actually unique function calls. Yeah, sorry, I wasn't clear. How many unique arguments are there for Fibonacci? That's what I'm analyzing. So maybe unique. So I'm going to call it with n minus 1, n minus 2, n minus 3. So there's n unique arguments, down to 1, right? Or down to 0, I guess. So I guess actually technically it's n plus 1, right? Because it's all the way from n down to 0. Yeah, so let me be a little clearer about that. Unique. If n is less or equal to 1, then no, I think that because of the way I numbered it here. Yeah. Well, as computer scientists, we start counting at 0, right?
Why we are not having cost of repeated arguments, because we will call n minus 1 multiple times, right? So like in that example, we have n minus 1
Yes, but we're going to assume that we're going to share it. So like what happens here, so that's a very good argument, question. So what's going to happen, right, is we're going to call it on n here. Okay, and it's going to call it on n, I'm going to put it this way, n minus 1 this direction, and n minus 2 here. And then n minus 1 is going to call it on n minus 2 and n minus 3. So I'm drawing it with sharing now. And n minus 2 is going to call it n minus 3 and n minus 4.
But your implementation doesn't say that, right?
My implementation, that's the point of view, is I'm going to say that let's just assume this happens magically. Okay? Remember, we're talking that the whole point of this class is we're trying to think more abstractly. We're not thinking at the implementation level. And then we have a provable implementation bound that says, if this is the case, we can then match these bounds. Okay? So we have to then show a provable implementation that says we can actually, given this analysis that we're doing, we can actually implement this efficiently. Yeah?
Sorry if this is obtuse, but the order of evaluation matters, right? Like we can't rely on the memoization unless the memoization exists, right?
What do you mean? Remember, this is purely functional, so order of evaluation doesn't matter. If that's what you're asking. I'm not.
So in the graph you just drew, n minus 1 is relying on all the n minus 2, right?
Yeah. So this is supposed to represent a DAG, right? So if this is a DAG, and what we're saying, what I've basically analyzed here is the size of the DAG is the work, and the depth of this DAG is the span. Now it happens that in this case they're exactly the same because basically the longest path goes through every single node in this DAG, right? The longest path, it zigzags back and forth like that. Do you?
Yeah, it's just not clear to me how the order of the hash table construction is happening.
Yeah, we'll talk a little bit more. We'll talk about the hash table later. Okay, so what I'm first going to do is show the analysis technique, and then we can talk about the hash. The tricky part of the hash table is we actually want this to work in parallel as well, right? So in fact, I'm first going to show how the hash table, now sequentially, how's the hash table going to work is I'm going to make these calls, I'm going to evaluate them, so I'm going to start evaluating this, and I'm going to keep recursively calling, and then on the way back up, I'm going to basically fill the hash table. Okay, so if you actually look sequentially, what would happen is this would call here, this one would call here, this one would call here, this one would call there. And I'm actually not filling anything in the hash table until I get the bottom, and then the hash table will be filled on the way back up. Okay, the memo table. And then when I get back up to the top, I then make the call to n minus 2, and it's done. It's there, right? And so I don't have to then compute it, and then I'm done with the whole computation. If that makes it clear. So the point is that this is my efficient dynamic program for Fibonacci. I have to assume a cost model where I'm going to recognize sharing, and that's partly why I assume the integer arguments, because I have to have some equality to figure out that it's sharing. And then this is the analysis. Now, of course, we all know that if we didn't do the sharing, Fibonacci would be exponential time. In fact, what is the actual time? What's the subscript in the exponent for Fibonacci, for the work of Fibonacci? It's not 2, yeah. It's the golden ratio, right? And which also, Fibonacci of n is approximately, the golden ratio to the n, right? So the work is the same as the value of Fibonacci. Okay, a second problem is going to be the minimum edit distance. which I'm going to refer to as MED for minimum edit distance. Okay, what's the minimum edit distance? I'm given two strings, and I want to know how many edits it takes to get one string to another. Right? So this is used all over the place in practice. This is what all of you have used either Git or SVN or any of those things. Of course, they use minimum edit distance to figure out the change logs to put in. If you've ever run diff in Unix or any of these things, it shows up all over the place. Okay, so we're given two strings. How many inserts? Let me call these S and T. So we're looking for the best case. We want to know the minimum number of insertions and deletions. Okay, how many of you have seen this problem before? Okay, most of you. Good. So this is another classic dynamic program. And so let's just look how this works. So this one is going to be parallel. And so what we do is, so the standard recursive approach is basically you start at the two ends. So you have two strings, our S and T. And you can start at either the beginning or the end. We're going to start at the end here. We're going to look at the two last ones. If they happen to be equal, then we can just erase them both and say we haven't paid any cost. Then we look at the next one. If the whole string is equal, we'll end up with no cost at all. We'll just keep erasing them. Now, if they're different, this one's A and this one's B, for example, there's basically two possibilities. Is that in order to get from S to T, such that the end of B is the same as the end of T, there's only two possible things that could have happened. Is we could have had to delete B, and maybe there was an A, the next one was an A. So we either had to delete B or we had to insert A. Okay, so we either, in order to get this situation, to convert from S to T, this one now ends in a B and that one now ends in an A, I either had to have at some point deleted this B or inserted that A. And those are the only two possibilities. And so what the recursive solution is going to be is we're going to take the best of the two. Now, sometimes in my undergraduate class, I get the students who think, oh, maybe I can be greedy. Maybe I can just guess that I have to delete this B, or guess that I have to insert the A. Turns out that doesn't work. You're going to end up, if you guess wrong, you're going to just completely mess up. Okay? Or you're going to have to come back and start again, which is the same as saying I'm just going to try both. So we basically try both. So the recursive routine is basically, if the last two characters are the same, I just make a recursive call that's one short on each side. Otherwise, I make a recursive call that's one short on either one side or the other, and add a cost of 1. Because the cost of either deleting the B or adding the A is both 1. So I have to add a cost. And that's the whole structure of the program, right? So I got fun. MED of S and T equals let, and I'm going to use a helper function here because S and T are strings, okay, and I want to be able to compare integers. So what I'm going to do is just keep an index into my strings, okay. So we can imagine these are actually sequences. So that's one sequence, and this is another sequence, which represent our string, and we have some index into them. So let's have this helper function. So f fun of, let's call it MED prime, because we always add primes for helper functions here. And so we have MET primes, and it takes an I and a j. And that's going to be a finger in here. So this will be my I into S and my j into t. And what this means is I'm currently considering the string that's up to I. Well, actually, technically, I guess it would be to the position before I, from 0 to I minus 1. Because, again, we're 0 based here. And the j represents from 0 to j minus 1. So we're going to start out with I equals the size of S. And the size of S points 1 past the end because we're 0 based. And we're going to start out with j equals the size of t. Okay, so we're going to need some base cases. So we're going to have a case ij of, and let's say one of them is the first one's 0 and the second one's j. In fact, I don't even need to writing j is redundant since I already know what j is. So let me just put an underscore here. So what's the edit distance of a 0-length string with a string of length j? J, right? Because this is about j inserts. If S is empty and I have to get to a string, I have to just insert them all. Okay, what's the edit distance of an empty with 0? I, good. Perfect. And then what's the difference of, I guess, the other case? In fact, let me just write that. Get my ML syntax right here. So in this case, I know that neither I or j are 0. So I and j are both greater than 0. So what's this going to look like? What's the first thing I have to test for? Yeah, I have to check if they're equal. So basically, I'm going to have an if S subscript I equals T subscript J. Yeah, I apologize if I have some off by 1 errors here. I realize now maybe that should be I minus 1 and j minus 1. Probably, I think, just because I'm 0 based. Otherwise, when I first call it on n size of S and size of t, I would just disrupt the nth element, size of S element here, which would be out of bounds, right? Okay, I think that's right. Okay, so if this, then I basically recurse on MED prime. That's my helper function of I minus 1, j minus 1. Okay, we agree with that. Else, what do we do in this case? Yeah, we take the min. We take, we'll take 1 plus. We pay 1 for an edit. This is either an insertion or a deletion. And it's the min of 2 recursive calls, either MED of I minus 1 j, in which case this one corresponds to moving my finger here, which corresponds to a delete on S. So this is sort of a cost of a delete. And or it's an insertion into T. So that would be MED of I and j minus 1. Okay, and I unfortunately left okay, I guess I can continue the code. There's an in here, right? Because there was a let at the very beginning, and I just have to initialize this on MED of the size of S and the size of T. Okay, that's the code, right? We're done. Mm-hmm.
The else in the mid, is that MED prime?
Yes, thank you. Yeah, otherwise it won't type check. Okay, Python would happily accept it. ML won't. But Python would just crash at runtime. So that's our recursive solution. Now this would take exponential time if we actually try to run it without taking advantage of sharing, right? Because we basically, if in the bad case, maybe we'll never match. Maybe the two strings are completely different, right? So in the bad case, we're going to basically make two calls. They're going to make two calls. And we're going to have some giant recursion tree that's something like, in fact, the depth of the recursion tree, well, we're going to look at that in a second because that's going to be the span. But it's going to be high, and it's binary, and so this will be exponential time. So we have to take advantage of sharing to get a good performance here. But as it turns out, we're going to get some good sharing. So we'll do that. So let's now, so that was step one, the recursive solution. Step two was span. So what's the span of this function? Again, let's not, for span, we don't have to worry about sharing at all. Any ideas? Is it log n or? It's what? S, yeah, size of S plus the size of 2. Perfect. All right, so it's going to be size of S plus the size of T. Why? Because every recursive call is going to remove something from S, or I'm going to remove something from T, right? So on every step, I reduce this sum by 1. Every recursive call. So after this many recursive calls, I've reduced them both to 0 length. And I go to the base case. Is that clear? So coming back to, unfortunately, I erased my tree. So basically, we now have this binary tree. And it's really bad because the depth of it is something like the size of S plus the size of T. So we get some, if we didn't take advantage of sharing, this would be a really bad runtime. So it's linear span. Linear in the size of the inputs. And that's what it is. So that's going to be a span. When we analyze span, that's it. We're not going to get logarithmic. So we've talked about how ideally we'd like polylogarithmic span. But there's a lot of algorithms where we can't. Parallelism, which is, remember, if you remember, that's the work over the span. So as long as the work is much higher than the span, we're happy. Okay, and that's going to be true in this case. So we have number of unique arguments. Can someone tell me how many different arguments we can have to help a function here? Is that size of T? Because we same thing for the second J. J ranges between 0 and the size of T. Okay, so this is, I'm just going to put an order. Well, I don't need the order for now. Well, let me put an order because, like I said, technically it's +1 and +1. So, and then the cost of each, the work of each, I should say. What's the work of each of those? And again, by the work of this routine, I mean I'm removing the cost of the recursive call, just all the glue that's around the recursive call. What is that? Constant, right? Because again, there's a couple comparisons, a couple minuses, and a plus, some small number of operations in there, right? So constant work. Per call. So the work equals order size of S times size of T. So what's the parallelism? Well, it's basically the product over the sum. So if they're both about the same length, that they're both about the same length, and let's call that length n, then we get n-fold parallelism. If they're both about the same length, then the work is n squared, and the span is n, where n is the length. So we've got a work that's, significantly higher than span. Now I should point out, you might say, well, is this really an efficient algorithm for MED? Theoretically, no one knows how to do better, even sequentially. Okay? In fact, there's various conjectures. Now, there's lots of special cases that you can have. If the strings are almost equal, you can do better. And under various approximations, you can do better. But it's an open question of whether you can do sequentially any better than n squared work. So this is a good sequential algorithm, and we get a significant parallelism out of it. And this is our way of analyzing it. Any questions here? Okay, what problem should I do next? What's your next favorite dynamic programming example? Knapsack. Okay. I knew that was going to be the answer. Okay, I'm going to do something slightly different because you all know knapsack, but it's very much the same flavor. And it's actually maybe a more practical problem. It's called the subset sum problem. It's used in cryptography in a lot of different places. It's basically just an unweighted version of knapsack. It's sort of like we have knapsack. So knapsack, you assume you have a bunch of items. Each of them have a weight, and each of them have a value. Right? And then we want to know the biggest value we can get by putting all those items together. This is an even simpler problem, which is equally as hard. It's theoretically NP complete if we don't bound. So you might know that knapsack is NP hard if you don't bound the size, the weight by a basically polynomially. Right? So if you allow for exponential values in the weight, then it's going to be exponential. So, but what we normally do is we say that the weight is going to be some polynomial, which practically speaking, you probably don't want to carry around an exponentially heavy backpack, right? So subset sum is we're basically given a set of integers. Let me call them natural numbers, so they're non-negative integers. And we'll call that S. And what we want to do, and a K, which is also an element of the natural numbers. And that's the sum. And what we want to know is if we can get any subset of S which exactly add up to K. So I guess it's slightly different than the knapsack. Knapsack you say, well, as long as it's not more than K. Here we want to know, is there a subset of S that exactly adds to K? So I'll write that down. You just use set notation for subset here. So that's our question. So it turns, like I said, if for arbitrary k, this is an NP-hard problem, but if we parameterize the cost in terms of k, so what we're going to do is we're going to basically generate an algorithm where k shows up in our cost, in our work, and I guess also in the span. And so if k happens to be exponential, well, then it's an exponential algorithm. But as long as we know k is reasonable, then it's going to be an efficient algorithm. So again, what's the recursive structure of this algorithm, well, going to look like, do you think? Again, we're going to design an algorithm that naively will be exponential time, and but if we recognize sharing, we'll be much more efficient. So what's sort of, the exponential time one is sort of a brute force. So what would be a brute force way to decide whether some subset of this set sums to k? The question at the back? Yeah, so the idea is we're going to try both. We can either remove it or we don't remove it. And so we're going to try both. So what we know is that any subset, and we look at any element, either that element's in or it's not. So we just try both. We say, try it with it in, try it with it out. So it's like the minimum edit distance where we say, well, try deleting the last element or inserting the last element in T, deleting from S or inserting from T. Here we're going to say either include it or don't. And then we take the best of the two. Well, not in this case, we don't take the best. In this case, we check if any of those two lead to a correct answer. So here we're going to have fun of SS. For SS stand for subset sum. Okay. Unfortunately, there's going to be too many S's going around here, but that's okay. And it's going to look very much the formulaic. At some point, these things become formulaic. It's going to look, oh, I erased the code for sub, sorry. It's very much like the code for MED. So we're going to write a helper function because we have to, this is a sequence here, right? That's, or set. Let's say I represent the set as a sequence, right? So this, I'm going to be able to index this from 0 to the length of S minus 1. And I'll do that with an index I. So we'll convert this to a helper function, SS prime, and we're going to have S, I guess I. So I is going to, once again, it's going to point to my position. So here's my initial set S, written out as a sequence. And my I is going to point somewhere in here. And I guess, once again, because I'm 0-based, if I point to I guess I'm actually referring to the element right before it. And once again, I'm going to have some cases. I'm going to have case I, k equals of. And once again, I have the possibility of I being 0 and the possibility of k being 0. What's the base case if I is 0? Remember, I of 0 means our set is empty because now I'm pointing to location 0 and there's nothing left before it. So if our set is, well, actually, let me write it the other way around because this way is messy. So let me write it first, putting this one 0. This one's true because there's obviously a subset of whatever my set is that adds to 0. What's that subset? Well, the empty subset. I don't even care what the weights are. I just say I'm going to include none of them. So this one's trivially true. Now, given that it's not 0, so in this case I'm going to say this is 0, and I know this one's non-zero, because if it was 0, I would have gone through here, and that's why I switched the order. So now we know the second argument is non-zero. If this one's 0 and that's non-zero, what does this return? False, right? Because there's no way I can add up to some sum with no elements to add up left, right? So I'm in trouble at this point, right? Or, once again, it's the else case, which means they're both non-zero. There's actually one if we have to do here because we want to make sure that we don't make the k negative. Because if we make the k negative, I guess we could probably make that work by changing the base cases, but it'll just become much messier. So we're going to check that if we want to make sure that if we include the element, that the element's value is not more than k. We basically want to add up to k if that element, the ith element, the one we're currently looking at, okay, I guess it's this one here, if that one, let's say, is 23, and if my k is 17, I know I'm not going to include this, right? Because there's no way that I can put the 23 in and 17. So I'm going to do that little check, which basically says if s, and I guess this is I minus 1 again because we're zero-based, is greater than k, what do I do in this case? I recurse, exactly, I recurse on just the problem. I'm not going to include this, so I just recurse on SS prime with I minus 1. So I basically don't include, go to back 1, and the same k. I don't adjust k because I didn't add that element. What am I missing? Oh, thank you. Hopefully the compiler would have found this error. Once again, maybe in Python it wouldn't, I don't know. Sorry for bashing Python. So else, well now I could include it, and now it's the two cases, right? So I'm basically going to say I'm either going to include it, I'm going to not, and if I include it, I'm going to have to subtract something from the weight, from the k, and if I don't, I don't. So I'm basically going to say either or. So make two calls, SS prime, on, in both cases, is I minus 1. Right? And in one case, it's going to be k minus a. So this is I include it. Oh, well, not a here. What's it's yes, this thing here, right? Or I don't include it, right? So this is all, I guess in ML it's or else. Let me just leave it as or here. So SS prime I minus 1, and I don't include it. Okay. And that's all the possibilities, and then in this case I can squeeze in the in, and then I just call in SS prime of my original I is just the length of S, and my original K is, well, it's K, same thing, just passing. Oh, and, yeah. Okay, that's the whole thing. Okay, I'm done at this point with the code in some sense. Like I said, of course, the implementation is going to have to deal with figuring out sharing, and there is going to be sharing here. But that's enough to, if I have a smart, runtime system compiler, then I'll be done at this point. Any questions about that code or? The knapsack problem looks very much the same. This is, of course, very similar to the knapsack problem. So that was our step 1, writing down our recursive routine. We probably, in order to know it's dynamic programming, we probably want to recognize that there's going to be some sharing. Well, again, we're going to have a similar argument. I can only take values from 1 to the size of S, and K can only take values from 1 to original K, or 0 to the original K. Well, I guess both from 0 to that. So we know there aren't that many different unique function calls. So we'll look at those specifically, how many in a second, but first we do the span. And like I said, for the span, we don't even care about sharing. What's the span of this? What is it? T? K? It's maybe not K. Size of S. Okay, the reason that it might not be K is because the recursive calls don't necessarily take any value off of K. So K could stay the same for multiple recursive calls. And so we can't argue that that's somehow going down. But we can argue that that I is going down because the only recursive calls always subtract exactly 1 off of I. Right? So in this case, the span doesn't even depend on K at all. It's just going to be order size of S, right? So again, you can view this as if you wrote this out as a recursion tree, it's going to be like exponential size because, again, we're making 2 function calls and 2 function calls in this second case, and this whole thing is going to be size of S deep. So if we don't take advantage of sharing, we're going to be in big trouble. It's going to be exponential work. Okay, what's the number of unique arguments here? An upper bound on it? Yeah, it's the size of K times the size of S, right? Because the first argument, the I goes, again, I guess it's plus 1. The I ranges from 0 to the size of S, and the K ranges from 0 to K. So it's a size of S times K. Maybe both of them. Let me this time I'll put the plus 1s in there for good measure. Okay, so that's the number of unique arguments because of just those range. And of course now it should be clear why using integer arguments helps us, because it often makes it very easy to bound the number of unique arguments because we just talk about the range from, we know what range those can take on and we can simply analyze it. And the cost of each argument, the cost of each call, again, not including the recursive part. Again, this is order 1 because, once again, we have a few conditionals, a few comparisons, a minus and an or, not much else. And so this is going to be order 1. So the work is the product of those two, which is order size of S times K. So what's the parallelism of this K? Because it's a work divided by the span, so the parallelism is K. So that's about how many processes we could make use of. So if K is often K is some polynomial number. So when this, in the application of this to in cryptography, and the reason it's helpful in cryptography is you might try to encode that think about it, you say only the person who is supposed to have the sequence knows the subset that will add up to S. And they can prove that they have the sequence, a sequence by doing that. Now, in order to be useful in that case, you have to make K so large that it's impractical to run an algorithm with this much work by brute force. Anyway, so the parallelism is order K. So we have both of these algorithms are reasonably quite parallel. Okay. Okay, I guess the next thing I wanted to do is I'm going to give you a problem and let you solve it, again, in groups of 2 or whatever, however, groups or by yourself or whatever, using the similar technique. So all you have to do is to come up with a recursive solution which of this flavor here, which does which has some sort of sharing, etc., and come up with what the work and span of that is. So let's look at some problem. We have to give every problem a acronym, so this is a list problem. So it's the longest increasing subsequence. Okay. In this case, the subsequence doesn't have to be contiguous. So by a subsequence, I mean that any basic subset of A's elements in the same order. So, for example, let's say I had 10, 22, 9, 33, 21, 50, 41, 60, 80. Can someone tell me what the longest? So I'm allowed to basically pick any of them. So one increasing subsequence would be 50, 60, 80. Length 3. Okay, so I want something better than length 3. I could pick 9, 33, 50, 60, 80. That would be 4. Does anyone know what the longest is? If you think you have I'm just asking you for this example. Then in a second, I'm going to ask you to actually write a dynamic program for it. But can someone tell me what the best is? Yeah?
10, 22, 33, 41.
Good. That's the answer. There's probably other solutions, I guess. 50. Yeah. There's probably lots of solutions. I don't want to know all of them. All I care about is the length. So the answer is 6. That's what I care, 6. I don't actually care what the positions are. I just want to know what the length is. So answer equals 6. Okay. So what I want is a dynamic programming solution to this. And ideally, the work is going to be polynomial, and the span is going to be linear. So I'll give you a few minutes, and you can work off in groups.
See how much of this code can reuse. So we'll have a list. Now we get our sequence then.
I think that sequence is not right over
Okay. And again, we will like to do this better. So again, we would like to do this level function. So here we'll call it subtract, and you again have an index, but we will also kind of record what is the value of the last number you can take, and then we'll do some cases here. So in the case where through all our sequence that we have done. So we will add 0 to the sum we have calculating on the form. And in the other case here, we will also first look on what is the next element we're going to pick. And instead of this k, then we're checking. So now we're going from behind, and then we have to have a decreasing sequence. So we kind of can't pick the element if it's larger than the last element we added. So in that case, we just call it recursive. So S prime I minus 1, and then keeping the same n. In the other case, then we have two choices here. So we could either take that element as part of our sequence or not. So what we want to do, we would like to return the element here, and that should be the max. If we take it, then our sequence increased by 1. And what will happen if we take it? Well, then we will call this recursive function I minus 1. And now the last element we picked is not n, but is of I minus 1. And the other case being we didn't pick it, so we don't have to get to add this 1, but instead we kind of can keep our last element picked as n, right? So, and then we kind of have to start this off with something. So here we call x prime, and then this should be our length of it. And then doing it this way, we will kind of have to put infinity here or our max in. So is it clear or any questions?
That's right. Wasn't exactly my solution, but this one we have for this one. Okay, good.
Do the other way.
Okay, so how many unique calls are there?
Oh, yeah, maybe to that part, two different solutions. So different calls, so there can be span would be what's the size here of S, right? We are decreasing the number S here each time, and so span yes balls, what should they be? That should be, so we have the, again, S bubble here, and here we'll kind of, should that then be about
So that was the way you've written it, that's a little trickier, but it's still, there's only n possible values that the SI minus 1 is going to have, right?
yeah.
They're not going to be, unlike the first argument, which is between 0 and n.
Yeah.
It's
So-
going to range any number, but
It
there's
should,
still
yeah,
only
be-
n possible values it can have, right? The unique calls is S, yeah.
It's squared, right?
It's squared.
Because we get S from the I and here again minus.
That's right.
Minus cost per call is again over 1.
Right. So the work is in squared.
Yeah, and parallelism will be yes.
Good. Exactly. Thanks. Okay, great. So, keeping up. So yes, if this solution is correct, it's a little trickier to analyze because we have to be a little careful with the second argument. We can't say its values are between 0 and size of S because it depends on the actual values of these SIs, which could be arbitrary big. Okay, but what we do know is that there's only size of S different possible values here because there's only one for location 0, 1, 2, 3, 4, 5, etc. So the number of distinct values here is bounded. So they can be arbitrarily large, but the number of different ones bounded. So exactly, so the number of possible values here is S because they've increased from 0 to n, or maybe be s size of s plus 1, and the number here is the size of s. And like on the other cases, as mentioned, we're basically saying we either going to include it in the, or not, right, in the two cases. So that's correct. So we've analyzed another algorithm. It's once again parallel. It gets the parallelism is order s, and it's got a similar flavor. Okay. Any questions about this particular problem? Okay, so given we only have 3 minutes, I'll finish here, and what we're going to do in the next one is we've been talking about this abstractly, right? So we want to know how we're going to actually implement this, right? And so I'm going to give you some hints on basically some idea of how we're going to implement this under the hood. First I'll talk about how to do it sequentially, and then we'll talk about how to do it in parallel. And the goal is basically to get something that's going to give us the work and span that we can use it as we've always been used. And so ideally we're going to be able to take the work and span and do, say that the time is going to be basically order, work over processes plus the span. Okay. So you want to be able to map it onto a parallel machine in that sort of setting. Now it turns out that in order to do this, we have to do something that's a little bit more advanced than the simple work stealing. We have to basically suspend jobs and restart them. In fact, what we're going to do is similar to what's needed to implement futures, or what's sometimes called promises, and so we'll talk about that. So I'll spend the next lecture talking more about how we actually get parallel implementations. But the idea, once again, from an abstraction point of view, and that's, we're trying to get our students to think this way, is you should be, as if someone's designing an algorithm, you don't actually need to know anything beyond this. What we covered here is enough to analyze these algorithms. We're done at this point. Someone else, which we're going to do ourselves, will do the job of doing the provable implementation. We'll do the job that says, if analyzing it this way gives you these bounds, then when we run it on a machine, we get those bounds. Okay, that's the idea of the provable implementation. Again, it's this two-phase thing. You give some abstraction of costs. And I haven't actually shown a formal cost semantics with this, but we could write down a formal cost semantic. You have some abstraction of costs here, which is what most people work in. And then you have the compiler, which is the lower-level thing that someone does once. Someone does this conversion from the abstract cost to the thing once, and then you just don't worry about it. Okay? As opposed to every time we write down a new dynamic programming, we have to think about, well, how do we do the memoization, and which in sequential maybe it's not that hard, right? But as you can imagine, to do this memoization in parallel is quite hard. And if you had to think about that every time you wrote a dynamic program, you'd be in trouble. Okay, so that's what we'll spend the next lecture on, and we're off to your break now.